Okay, so the last component of these special unit vectors we want to look at is called the binormal vector. Now, we've looked at the unit tangent vector, and we've talked about the principal unit normal vector. Let me see, let me write these down. The unit tangent vector. Oops. I'm going to stay with t's back in 3 space. The principal unit normal vector. And now let's take a look at the binomial vector, because these three together are kind of special. Now, the vector b of t, which we use to denote the binomial vector, is equal to or is defined by t of t cross n of t. And it's called the binomial vector. And it is a unit vector, and it's actually orthogonal to both t of t and n of t. So the binomial vector is orthogonal to both the unit tangent vector and the principal unit normal vector. Now, this is given simply by the fact that this is a cross product. I'm going to say here, so orthogonal to both, say by the definition of a cross product. Remember the idea of torque when we introduced the idea of the cross product? So that's what we're getting here, is the same sort of a thing. So I can also say then that clearly, because of the cross product, b of t is also a unit vector. So when I add b of t to the trio here, all three of those guys are in fact unit vectors, and they're kind of special unit vectors. All right, so let's go ahead and take a look at an example here. Now, find the vectors tn and b given r of t is defined as being cosine t, sine t, natural log of cosine t. Well, the first place, well, I'm going to add to this also. At the point 1, 0, 0. So I want to see what's going on my curve in respect to these three special unit vectors at this specific point. Well, let's just start going after the components. T is defined as r prime of t over the magnitude of r prime of t, the unit tangent vector. That's going to be the vector, let's see, negative cosine of t, negative tangent of t, divided by the magnitude, which gives the square root of c negative cosine t squared plus, oops, that's not cosine, that's sine. Hate it when that happens. Derivative of cosine is negative sine. So this is negative sine t squared plus cosine squared t plus a negative tangent t squared. So that's going to be the vector, see, negative sine t, cosine t, negative tangent t divided by sine squared plus cosine squared is 1. This is tangent squared. This is going to be the square root of 1 plus tangent squared, which is secant squared. So this is the square root of secant squared, which is just secant. So kind of ran out of room here. I guess I'm going to need more space on here. I'm going to say this is equal to the vector negative sine t, cosine t, negative tangent t divided by secant of t. Now remember, secant is 1 over cosine. So let me see. Is that going to help me? Is it going to make matters worse? Yeah, what the heck. Let's go ahead and this, it may come in handy. This is same as 1 over cosine of t. So this is going to be the same as negative sine t, cosine squared t, negative tangent sine over cosine. So this is just negative sine. Now, if I look at this specifically at the point 1, 0, 0, so I'm going to evaluate this at the point 1, 0, 0. What does that mean to evaluate this at this point? Well, go back up to my original vector function, and the only way I'm going to get a 1 here for cosine is going to be if t is 0, because that's going to give me cosine of 0, which is 1. Sine of 0 is going to be 0. And cosine of 0 is 1. Ln of 1 is 0. So that will give me the point 1, 0, 0. So this is the same as saying that t equals 0. So for t equals 0, I will get the point, well, actually I will get the vector, the position vector 0, 1, 0, which, by the way, that's the same as j, the basis vector j. Not that that's important right now, I just thought I'd throw that out at you. Okay, so my unit tangent vector at the specific point will be the position vector 0, 1, 0. Now I need to go after the principal unit normal vector, n of t, which is going to be t prime of t, over the magnitude of t prime of t. Let me see, I've got this written in a couple different ways, so I guess I could probably just go ahead and pick what I think is going to be the easiest to take a derivative of. Nah, it doesn't make too much difference. I'm going to use this form right here. So I need to take the derivative of this guy. So just component by component. The derivative d dt of negative sine t of cosine t. The derivative of negative sine t is going to be negative cosine. So this is going to be negative cosine squared t plus, well, actually minus, but the derivative of cosine is a negative sine, so I'm going to have double negative, so this is going to be plus sine squared t. That's my first component. The derivative of cosine squared is going to be 2 times cosine of t times the derivative of cosine, which is negative sine. So it's negative sine t. And this last component is going to be the derivative of negative sine t, which is going to be negative cosine t. Now, since I'm interested specifically at the point 1, yeah, there it is, a point 1, 0, 0, I'm just going to evaluate this when t equals 0. Let's see, I'm going to evaluate this at t equals 0. And what I do, don't forget, I still need the magnitude of this. But I'm going to evaluate this first for a reason. It's going to make life a little bit easier. When t equals 0, what I end up with is this vector negative 1 plus 0. This is going to be 0. And this is going to be negative 1. So this is t prime of t at t equals 0. So when I divide it by the magnitude of this, well, the magnitude of this at t equals 0 is just going to be the square root of 2. Square root of negative 1 squared plus negative 1 squared, root 2. So I could write this principal unit normal vector as, getting a little bit messy here, sorry, of n of t. Actually, this is n of 0 because that's t equals 0. And I really should put that in there. I really should call n of 0. Is going to be, let's see, the vector negative 1 over root 2, 0, negative 1 over root 2. Now, keep in mind, I am kind of taking the chintzy way out. That being, we're looking at this specific point. And so I'm not doing this as a function of t anymore. And And actually, I should make this t of 0. Just so we know what really vectors we're really looking at here. So the last thing I need is I need the binomial vector. B of t equals t of t cross n of t. That means b of 0, what's going to correspond with this point once again, is going to be equal to, oh, let's see, where's that vector? There it is. 0, 1, 0 cross negative 1 over root 2, 0, negative 1 over root 2. So let's go ahead and quickly find that cross product. And what I end up with is, let's see here, I, j, k, 0, 1, 0, negative 1 root 2, 0, negative 1 root 2. Okay, so for I, I'm going to have negative 1 root 2 minus 0, so that's negative 1 root 2 I, minus for j, I'm going to have, what am I going to have? 0. So this is 0 j. Plus for k, I'm going to have 0 minus a negative 1 root 2, so that's just 1 over root 2 k. So I end up with the vector negative 1 root 2, 0, positive 1 over root 2. So this is, in fact, the binomial vector evaluated when t equals 0. Now, together, the vectors, the very special vectors, unit tangent vector, principal unit normal vector, and the binomial the binomial vector make up what is known as the TNB frame, the TNB frame, obviously TNB. So very quickly, I'm going to jump into Maple, and let's take a look at the TNB frame, specifically at that point that we're looking at the point 1, 0, 0, which of course implies that t equals 0. Okay, so let's start off with student. You know we're going to need that. And let's do with, actually I did not want that. I'm sorry. I didn't want with student, I wanted with plots. And rather than simply with student, I needed with student vector calculus. There. That's going to give me all of the commands that I'm going to need. Okay, so let's see, I've got those. So let's go ahead and start putting this together. Okay, in the interest of time, I went ahead and just typed all these commands in. There they are. You can pause it and take a look at it. But I set up A, B, C, and D. A being my space curve, B, C, and D being my three vectors, the tangent vector, the principal unit normal vector, and then the binomial vector. So if I take a look at a display of these, let's see if this makes any sense, what's going on. Okay, so here's my curve. Here's a positive x-axis, positive y-axis. This will be negative z, positive z's coming up this way. And when t equals 0, I'm actually at this point right here on the curve. Let's go ahead and make this a little bit bigger. It may be easier for you to see what's going on. There we go. Now remember, these are position vectors. So think of this, grab this point and move it right over to the curve right here and take a look at where these vectors are pointing. Now, first of all, I'm going to spin this down a bit. I think it's not too hard to imagine that this is, in fact, my tangent vector. Remember, my tangent vector was 0, 1, 0. It has length 1 on the y-axis. It's 0 every place else. So I think this is pretty clear that this is the tangent vector. Now, which one is the normal vector? The one that points in the direction of the curvature. Well, if you look at this curve, see it kind of comes up and back down. It's twisted. It's not in a flat plane. This thing's twisted. So curvature is in this direction, which is this guy right here. And then this is the binormal vector. Now, first of all, these two vectors, the unit tangent vector and the principal unit normal vector, or sometimes simply referred to as the normal vector, are supposed to be orthogonal. Well, if we spin these around, I think we can probably convince ourselves that those really are orthogonal. Just by visual inspection. It looks like, yeah, they probably are, in fact, orthogonal. And actually, this view even gives you a better idea that this is probably tangent. And it is pointing in the direction of the curvature. This binormal vector is supposed to be orthogonal to everybody. Well, clearly, if this is the binormal vector, it looks like it's orthogonal to the first vector, but boy, I'm having a tough time convincing myself that these two are orthogonal. No way. Well, actually, way. The problem is in the way that Maple's displaying this. You can see from here to here is 1. Here to here is 1, 2, 3. So the axes are not at the same scale. So let's go ahead and I'm going to right click on it and scale constrained. Now 1 on the y-axis is the same as 1 on the z-axis. And now I think you can see by looking at just these vectors that they are in fact orthogonal to each other. So what I'm going to do, just so we can see them better, is I'm going to go ahead and get rid of my space curve. Don't really need that. And see, here's my 3 orthogonal vectors. And by spinning these around, I think it's pretty clear. You can tell that these guys really are orthogonal. So one more quick thing. Let's go back and put my space curve back in. And I'm going to take out vector D. And D is the binormal. So all I should get now is my tangent and my unit normal vector. And I'm going to unconstrain these, just so that we can spin this. And I encourage you to fit around with this. Get this on your computer. Fit around with it. There's a positive Y and positive X, negative Z. And you can see by the curvature here, the way it twists, that the curvature at this point is more of a downward thing. And that's what this vector is giving you right there. So now I'm going to go back and put in vector D, the binormal vector, and remove the normal vector, the principal unit normal vector. And you can see that these two guys are in fact orthogonal. Now, what these really mean, well, we'll get this into this a little bit in a later section, because these are actually used to represent different things in physics. And we will take a look at that a little bit more detail in the future. Right now, what I want you to do is just see that these vectors really are orthogonal. And if you can imagine taking this off, well, okay, let me go back here and make this a C again, because these are really the two that make more sense to us right now, because curvature and tangent. If you were to take this and move it to this point right there, you can see the curvature and tangent.